So to take this test, you will have to connect to Zoom first, and then connect to WebWork, and you'll see the link in the homework problem. The last, I think, will be the exam 1. So the exam will be, you'll take this using WebWork. Exam 1 is on WebWork, like last semester. Okay, so now today we will just cover section 11.1. This section will not be on the test number 1. Test number 1, as you know, covers from 10.1 to 10.9. But we have to keep up with the syllabus. And next time, Monday, there'll be a review, test 1 review. Okay, so let's go to so now I go to Canvas as usual. And 11.1. So functions of several variables. Okay, so now again, can you confirm? Can you see it?
Yes.
Yes.
Thank you. Okay, so functions of several variables. Well, you are familiar with function of 1 variable. Now you may have functions of 2 variables. So here is the next kind of case. A function of 2 variables is a rule which assigns for each pair of numbers, for each 2 numbers, x, y. So those are the variables. Now you have 2 variables, x and y. In a domain, a real number z equal f of x, y. So again, z is a function of f, and function of f depends on x and y. Now, there'll be examples, of course, in a moment. Later, we'll have also functions of 3 variables, and you may have functions of any number of variables, but let's start with 2 variables first. So a function of 2 variables can be given by a formula. Well, for example, f of xy is x squared plus y squared. That's the function of 2 variables. A graph, well, you may have kind of just, you generate a table, and there'll be example in a moment. Or a graph, well, graphs is here, graphs are here. You see that the x squared plus y squared, if you have z equal x squared plus y squared, this surface looks more or less like this. So z equal x squared plus y squared, this would be looking like this. And table, you'll see the table on the next page. So now, usually we say that the domain of the function is the set of all x and y for which this is defined. So you could say that the domain of this function is everything. X ranges from -infinity to infinity, and y ranges from -infinity to infinity. However, you can artificially restrict the domain. You can say, well, I am interested in this function under this constraint that x squared plus y squared must be less or equal than 4. Then this will be a domain. So if you restrict the domain, so xy depends on the domain, and again, usually the domain is a set of all x and y for which this is defined, but you can restrict it artificially if you want. So here we restrict the domain of this function to x squared plus y squared less or equal than 4. Then the things will stop here. Here is 4. This is this x squared plus, if you take, well, we will talk about level curves in a moment. If you consider x squared plus y squared equal a constant, of course, that's a circle. You have small circle here, and the circle is growing as Z is ranging from 0 to 4. Now you hear this kind of the point 1, 1, 2 is so of course when you take x squared, 1 squared plus 1 squared, it's 2. So the point 1, 1, 2 is on the graph of this function. Yeah, because again, 1 squared plus 1 squared is 2. So the point 2, 1, 1, 1, 1, 2 belongs to the graph of the function. Now this table, okay, so you can kind of generate a table. You can have x here and y here. And let's say for x equal 1, 2, 3, and 4, and for y equal -2, 1, 4, you can compute the values, and kind of the function may be given by a table. So kind of you may find such things kind of just you see in applications that kind of just you see, let's say, the height on the surface of Earth. So you can squeeze the surface of Earth. That's a 2-dimension set. And then kind of the function is the height. And so you just measure the height at specific points, and the function may be given by such a table. So that's, you can encounter this in applications. So for example, what is value of 1 and -2? Well, that's 1 squared plus -2 squared, that's 5. And you put the value here. You can verify that you can compute all those values, and you can generate a table for any values you want. X can extend. Also, you can consider negative values and so on. So function can be given by a table. Something I mentioned, the level curves. What are the level curves? The level curves of the function are the curves with the equation f of x equal some constant. So again, function is z equal f of xy. If you put z equal to a constant, well, you'll get a curve. Yeah, you have just two variables, x and y. This is curve. And such a curve is called level curve. So for example, when z is 1, so consider again this function z equal x squared plus y squared. When z is 1, you have x squared plus y squared equal 1. Well, that's a circle with radius 1. So here. When k is 2, you have x squared plus y squared equal 2. Well, that's a circle with radius square root 2. When z or k equal 3, you have x squared plus y squared equal 3. That's again a circle with radius square root 3. So if you cut this surface by kind of those planes, z equal 1, z equal 2, z equal 3, you get a circle, you project it on the xy plane, and they look like this. So those are called level curves in xy plane. You project those curves into the things. So here those are the level curves. F of xy equal 1, that's a circle with radius 1. F of xy equal 2, circle with radius square root 2. Circle with radius square root 3. So of course, you can use those level curves to visualize the function. So for example, you already know the applications of this. When you see a map, well, level curves are plotted on the map. They correspond to the elevation. And the high elevation is usually kind of in red, marked in red, and low elevations are marked in green, and the elevation in between are marked in pink. So of course, the map is just a set of level curves, which tells you kind of the elevation of the position on the map. Elevation of Phoenix, for example, you see the green color. elevation of Grand Canyon somewhat higher, yeah. Or San Francisco Peak very high. It would be marked kind of by red things. So kind of just, you are more or less familiar with level curves because kind of just those level curves are used on maps. The surface of Earth is three-dimensional. You have X, Y, and you have the height. Of course, the map is two-dimensional, kind of just you project those heights using level curves. So level curves allow us to visualize how the function looks like. So again, here is another kind of curve, another surface, another function is equal f of xy. This blue one has this graph of this function is here. And of course, when you cut things by level curves, yeah, let's say z equals 6, z equals 5.5, z equals 4, and so on, and project, you'll get, of course, the circles, you projected this on the xy plane, and you get a map of this hill. You can say, well, that's a hill, and that's a map of this hill. So on the map, usually you would put here the red color here because that's high. This is very high here. You would put some green color here because this is kind of sea level or something. Those are level curves. Have any questions so far? So of course, level kind of functions in several variables are more complicated than one variable because you, even here, function of two variables, you need 3 dimensions to plot it. So that's usually non-trivial things. You will see in a moment very interesting functions as you. Also here, for example, you have graphs of functions. So those are the 3-dimensional objects, yeah? So that's a graph of the function. And then those are level curves. If you cut the function kind of by slices, but for constant z, you see that, of course, kind of just you are getting circles. So this circle corresponds to this one, kind of, this big circle corresponds to this, and so on, kind of. So those are level curves of this. Similar here. Again, so the level curves look similar, but of course, on the map, you would put here the red color here. And you put green color here. So certainly kind of just you would see the difference. Yeah, that's kind of a valley. And this is kind of a hill. Valley, hill. So of course, the level curves looks similar, but of course, they have different heights. So again, just you would just mark this in red here and green here, and again the other way here, green here and red outside. Here you see kind of this saddle level curves look like this. This kind of things, the level curves look like this. Yeah, if you cut by constant z, you see that you get more or less line. So here, if you cut like this, you see that you get kind of hyperbola. If you cut down, you get hyperbola. We will get those equations for those curves in a moment. So those are examples of contour plots. Again, if you have some questions, just interrupt me at any time. So again, this function here is a very famous function. This is the saddle point. So this function is called hyperbolic paraboloid or saddle. Well, and the equation of this hyperbolic paraboloid is z equal x squared minus y squared. Very simple equation. And the graph of this function looks more like this, like a saddle. You can sit here. So of course, now you try to figure out contour plots. Well, so first, if z is equal to 0, well, you have x squared minus y squared is equal to 0, or this means that x squared is equal to y squared. This means that x is equal plus minus y. So when z is 0, you get two lines. Y equal x is this line, y equal x, and y equal minus x, because the equation is x squared, y squared is equal to x squared. So this means that y is equal plus y, plus x, or minus x. So you see one straight line here, straight line here. So those green level curves correspond to k equals 0. It's here. Now when k is equal 1, of course, you see that that's hyperboloid. So when k equal, this hyperbole looks like this. When k is equal to 3, that's again hyperbole. You have on both sides, here and here. Those are hyperbolas. Z equal 1, z equal 2, z equal 3, hyperbolas. When you have z equal minus 1, minus 2, minus 3, that's also hyperbolas, but now they look like this. So for example, k equal minus 1 is this curve. K equal minus 3, it's this curve, and so on. So that's a saddle, and those are the level curves. So those are contours. And the set of level curves is called contour plot. So that's a plot in 3 dimensions. That's a plot in 2 dimensions. It's called contour plot. If you know MATLAB, MATLAB has a command, contour. When you define the function, then using the command contour, you can plot those level curves. MATLAB will plot the level curves and put the values of the constant k corresponding to the z. So level curves, x squared minus y squared equal k. Those are, when k is equal 0, gives those straight lines, asymptotes. Y equal x and y equal minus x. Those are the asymptotes for those hyperbolas. All the hyperbolas go to those green lines as x goes to infinity or y goes to infinity. So for k equals 0, we get straight lines. And for all other values of k, we get hyperbolas. And again, here's some observation. Note that the values of k decrease as we approach the origin from the x-axis, and they increase as we approach the origin from the y-axis. So here, you have here k equal 1, 2, 3, they increase. But here you have k equal minus 1, minus 2, minus 3, they decrease. So here is some interesting example. Of course, you would not be able to plot it by hand. Kind of this was plotted using MATLAB. But look, the function looks like this. 3, 1 minus x, e to the power minus x squared minus 1 plus, and so on, kind of. So that's a very complicated formula, but that's a function of 2 variables, x and y. So of course, in general, this represents some surface. Well, this surface looks like this. Again, you can plot it using MATLAB if you want. The command is plot 3D. So you see this function looks like, so you see this function has some hills, and they are marked in red. They have valleys, they are marked in green. Yeah, so there's hill here, hill here, hill here. There's some saddle point, as you see here. For example, saddle point means if you move in this direction, you go up. If you move this direction, you go down. So you see, so that's the complicated surface. So again, to visualize the surface, you can plot the level here. So again, that's a surface. Think about those are the mountains, and this is the map of the mountains. Again, so that's the highest peak, looks like it's here, it's red. This is some medium peak, although this is medium valley here, and so on, kind of. And you have saddle point here, here, and here. So again, this kind of corresponds to a map. You see here those, when you move along such a curve, you are on the same level. Let's say, maybe, let's say 100 feet above sea level. Maybe here, when you move, maybe you are 1,000 feet above sea level, and so on, kind of. So surface, that's a visualization of three-dimensional picture, two-dimensional visualization of three-dimensional picture. Of course, that's kind of, yeah, that's a map. In some sense, you can say that's a map of this kind of just valleys and hills. A map of this region, kind of, which looks like this. So again, you can kind of identify local maxima here, here, and here. So maximums here, you see here. So M, capital M is local maxima. Lowercase m is local minima. So you see local minima somewhere here, 3 local minimas. And of course, here as well, yeah. And saddle points are at those coordinates, roughly speaking. So again, complicated function. To visualize this, the best thing is just to plot it. You just plot it, and then also just you make a contour plot. If you, that's a plot in 3 dimensions. Contour plot, when you look and here, you may have some good idea how the region looks like. Yeah. Here we'll try to identify a contour plot with a surface. So again, so here is the exercise. You have similar exercise on the web work, as you will see. Surface 1 looks kind of like this is this function is equal x squared plus y squared, kind of looks like this. Another surface, you have 2 valleys here. And another surface, you have 2 hills and some valleys and so on, kind of, yeah. And then you try to identify kind of which corresponds to which. So of course, 1 and 2, the contour plots are all circles. So of course, 1 and 2 are here. 1 and 2, yeah, if you see that the surface levels are all circles. And now which one is which? Well, it looks like this one corresponds to 1, yeah, so 1C, as you see, because kind of those circles kind of just are more uniform. Those circles here are changing fast. The small circle here, big circle here, yeah, so small here, big here. So kind of it looks like 2 corresponds to D. So 1C, 2D. This is easy, of course, yeah. If you see that here, if you cut it, of course, you get 2 valleys. So on the map, you would mark those regions by green color, and you would put red color here. So clearly, this surface 3 corresponds to contour B. And of course, here you see that you have, it looks like 2 hills and 2 valleys. Well, 2 hills, 2 valleys. I think hills are here, this one and this one, valley is here and here. So you would put on the map green color here and here. No, I mean red color here and here because those are hills. And here you would put green color because those are valleys. So again, you can identify, kind of, you can imagine how the contour plots look like, more or less. Again, any questions?
I'm just unclear how you can tell if it's going in or out based on the maps here, the contour maps.
If it's going in and up, well, looking here, kind of just to see, you cannot say this right away. When you would put a contour plot, the contour plot would put also the elevations here. So for example, it would put here 1, 2, 3, 4, 5, and then looking at the numbers, then you can figure out kind of what's going on. Also looking at the color, for example, if this is kind of in red and this is in green, this means, aha, that's a hill.
So typically these maps will have some color to them if we're having to look at them.
What did you say?
The maps or the contour maps, they'll have like, they'll be colored or have numbers.
Correct. They'll be colored, and also they may still kind of they may list elevation kind of on the map. For example, when you have Mount Everest, they will tell you that the Mount Everest is at whatever 7,000 something meters or something like that. I don't remember exactly, but kind of, so those levels may be also marked on the map. So again, if you plot this thing in MATLAB, the MATLAB will put you a contour, but not only contour, it will put the numbers, let's say 1, 2, 3, 4, 5, which correspond to those levels. And then, of course, looking at those numbers, if you see here, for example, 1, 2, 3, 4, 5, this means, aha, going this way, we are going up. So clearly, looking at this only, it's, of course, just you can figure this out if you compare this with this. But if only this is given, then it's not clear right away if this is a hill or a valley, of course. You need additional information. So this is all clear? Okay, well. So here now, let's go to some theoretical, again, definitions, some definitions and so on. So what I mentioned, unless otherwise specified, the domain of the function, in this case of two variables, is the set of all points, x, y, for which f of x, y is well-defined real number. So again, so that's usually how you define the domain. The domain is the set of all those points for which the function is well-defined. Of course, you can restrict the domain artificially if you want, and there'll be an example in a moment. So that's the definition of the domain. The range of the function is the set of all z's, z equal f of x, y, where x of y belongs to the domain. This symbol means belongs. X, y belongs to the domain. So here is the example. Find the domain of the function f of x, y equals square root x minus y plus 3 over x plus 2. That's the first example. There are two examples. Okay, so looking at the function, you see we have two restrictions. First of all, x minus y plus 3 must be greater or equal than 0. That's the first restriction. And second restriction is that x plus 2 cannot be equal to 0 because we cannot divide by 0. So the domain means, well, and then, okay, so now plot the line x minus y plus 3 equal 0. That's the line. So this is the line, x minus y plus 3 equal 0. This is the line. So now, on one side of the line, we have negative values, and you can check it picking one point. So for example, and here you have positive values. So for example, if x and y is equal to 0, you see, of course, that we have positive numbers, square root of 3. So this means that the domain is on the lower part of this curve. So the domain is this pink or this yellow region. In other words, x minus y plus 3 must be greater or equal than 0. When you solve it, this means that y must be less or equal than x plus 3, and that's this decision. Another restriction is that x cannot be equal to minus 2. So they put this thing as by this dashed line. So the domain is this yellow region with the exception of this dashed line. So this dashed line does not belong to the, so this is the domain of this function here. Yeah, this makes sense. So for example, if you pick up the number, let's say -3 and 3, of course you will see that if x is minus, it will be minus, if you put x equal y, so yeah, so this will be negative here. Yeah, so picking the number, if you pick the number x equal -3 and y equal 3, then you get -3, -3 plus 3, you get square root -3. Of course, that's complex number. So this point here is not in the domain. So when you have this kind of, have to decide which side of the line, you just pick one point, and this will allow you to pick up the side. So the domain is here. Again, this yellow region with the exception of this line x equal -2. This line x equal -2 does not belong to the domain. Here another, f of xy is y squared, natural logarithm x minus 2y squared. Of course, the restriction is that x minus 2y squared must be greater than 0, because the argument of the logarithm function must be greater than 0. So this means that x minus 2y squared greater than 0. And of course, to figure out how this region looks like, you write first you write a parabola, x equal to y squared. Has this, that's the function x equal to y squared. That's a parabola. And then, of course, you are on this side or this side. To decide where you are, here or here, you pick one point. Let's pick up the point 5 and the 0. Well, when you have 5 and 0, you have 5 or is greater than 0. Yeah, so the point 5, 0 belongs to the domain. So this means that the domain is everything here, of course, excluding the boundary. So that's why we put this in again by dashed line. Everything excluding the boundary. Now, you may think, what is the range of those functions? Well, it looks like the range can be everything. It kind of looks like, yeah, because this can be go arbitrary. Of course, that's always positive. But here, the x plus 2, picking x, let's say greater than 2 or less than 2, we can have positive and negative values. So it looks like the range probably is everything. And here, the range, it seems to be also everything, because logarithm is, can take any value, and that's a positive, but this can be positive, negative. So it looks like the range is everything here and everything here. But here, they didn't ask us about the range. But now, next example is, they're asking about the domain and range. So another example. Find domain and range, and that's a function, f of xy equals square root 4 minus x squared minus y squared. So of course, the domain is, this has to be positive. So 4 minus x squared plus y minus y squared must be greater or equal than 0. Well, this is equivalent that x squared plus y squared is less or equal than 4. And that's a disk with radius 2. So again, disk, everything inside the circle, and of course, the circle itself also belongs on to the domain, because x squared plus y squared equal 4 is a circle, but the circle belongs to the domain as well. So we put this by solid line. If we would have a restriction strictly less than 4, I would put this by dashed line. But here, the boundary of this disk belongs to the domain as well. So the domain is this set here, including the boundary. So that's the domain of this function. What about the range? Well, the range, of course, you see that this is always positive. So that's always positive. Now, if you would plot this function, you will see that it looks more or less like this kind of. And again, you see here kind of that, well, what is this, the biggest value this function can take? Because we have minus and minus, the biggest value this function can take is when x and y are as small as possible. Well, the smallest x and smallest y is 0, 0. So the biggest value would be f of xy equals square root 4, which is 2. So this means that the range is interval from 0 to 2. Yeah, function is of course is positive, but cannot be bigger than 2. It looks like this, as a matter of fact. This function looks like this. So the domain is this yellow set, and the range is the interval 0, 2. Here, on the other hand, the square root is always non-negative. So z is greater or equal than 0, and of course the largest value of z is 2. So the range is from 0 to 2. Again, sometimes it can be quite difficult to compute the range and quite difficult to compute the domain. You will see kind of in a moment 3-dimensional examples. This is just 2-dimensional, but things are getting more and more complicated when we go to more dimensions. Here in this class, you will deal only with function of 2 variables and 3 variables. And I think that's all. You will not have function of 4, 5, 6, or something like that. So just you will see function of 2 variables and function of 3 variables. So here is general introduction. You may have a function of n variables. So a function of n variables assign a number z to those variables x1, x2, xn. This is called n tuple. So x1, x2, xn are independent variables, and z is dependent variable. And you may have any number of variables here. N can be anything. So we discussed so far when n was equal to 2. When n is 2, you have x1, x2, but you may have more. And here is example of function of 3 variables. Z equal f of x, no, maybe some other letter. Maybe x, y, z, t, or maybe p or something, yeah? So f of x, y, z. So now independent variables are x, y, z. So that's a function of 3 variables. It's given by x squared, natural log of x minus y plus z. And some questions. Evaluate this function at the point 364. Well, you just substitute, yeah? So f of 364 is 3x squared, so 3 squared, natural logarithm 3 minus 6 plus 4. So this is 9, natural logarithm 1, natural logarithm 1 is 0. So certainly to evaluate the function, you just substitute the values into the formula for the function. So that's not a problem. Well, second, find the domain of this function. Of course, now the domain, well, that's a natural logarithm, so x minus y plus z must be greater than 0. So the domain is a set in 3 dimensions, set of all points x, y, z, such that, this line means such that, x minus y plus z is greater than 0. Of course, you know that's a plane, x minus y plus z equals 0, that's a plane. This plane looks like this green plane. So this means that the domain is this side or this side of the plane. You are on one side or the other side. And then kind of just picking some specific values, you see that you are on this side of the plane. So the domain is half the space. So it's kind of complicated thing. Yeah. So the plane x minus y plus z divides the space in 2 parts. The part of space above the plane constitutes the domain of this function. So those, and again, you can pick up one point to see.
Professor, I had a quick question.
Yeah.
when you have, for example, you have f of x, y, and z, and that equals something, for example, 0 in a, what does that 0 represent? Because typically when you have a function of of x and y, then the answer you get when you evaluate it is the value of z. So when you have x, y, and z in a function, what does the solution, or I guess the output, represent?
Oh, it depends on the situation. You will have the example in a moment, but let's think about this like this, that you have a functions of 3 variables, x, y, and z. And at each point of space, you are interested in the temperature. So you can say, okay, the temperature at this point is 60 degrees of Fahrenheit. The temperature at the different point is 70 degrees of Fahrenheit. So the function may represent the temperature, but it can represent a lot of other things, depends on the application. So kind of just whatever you think. Another example, the function can represent the density. You have some object, and kind of the object sometimes kind of has bigger mass in some regions and smaller in some other regions. The density is changing. So the function f of square z at any point may represent the density at the specific point. That's another application, temperature, density. And of course, there's thousands of applications. So depends what you want to model. You model some kind of physical phenomenon, and to do this, you may need function of 3 variables. So for example, another example, Navier-Stokes equation, you heard about this. So those are the fluid dynamics equations, and they depend on x, y, and z. And you may be interested at the velocity of fluid at specific point. So again, the function may represent the velocity of fluid at the specific point x, y, z, and so on. Again, thousands of applications. So the function can represent kind of just whatever you want to model. So this answers your question?
Yeah, that makes a lot of sense. Thank you.
So the domain is this part of the plane. Now, what is the range of this function? Of course, you see here that x squared is always positive, but natural logarithm can be positive and negative. So it looks like the range is everything. Yeah? The range of this function can take any value. So the range is from -infinity to infinity. So here, this example I mentioned, okay? So now, another example. The temperature in the region where there is a heat source at the origin is given by, well, temperature, T, is 1000 over x squared plus y squared plus z squared. And now we are interested in the region. So that's a domain. We restrict the domain. X squared plus y squared plus z squared must be greater or equal than 1. When this would be equal to 1, this would be a sphere of radius 1. So we are outside of the sphere of radius 1. We are outside the sphere of radius 1. We can be on the sphere as well. And the heat source is at the point 0, 0, 0. So we have some oven at the point 0, 0, 0, and we are interested in what is the temperature when we are outside the sphere of radius 1. And the temperature, well, okay, let's say the temperature is given by this formula. So for example, when we are on the sphere, the temperature is 1000 divided by 1, so that's 1000. Maybe let's say that's a degree of Kelvin or maybe degree of Celsius, doesn't matter. Yeah, so let's assume that that's in degree of Celsius. So on the sphere, the temperature is 1000. And of course, as you move away from the sphere, the temperature is going down. If x squared plus z squared plus y squared plus z goes to infinity, the temperature goes to 0, of course. So when we move from the heat source very far, the temperature is kind of getting smaller and smaller. So again, now we try to understand kind of what this function tells us. Well, we cannot graph this surface because we would need 4 dimensions. Okay, yeah. So to graph the function, you need 4 dimensions. Yeah, t, x, y, and z. That's impossible. But of course, we can think what are the level surfaces of this function. So the level surface means, well, put the temperature to some constant value. So the level surface is 1000 over x squared plus y squared plus z is equal k. K is constant value. So for example, if we pick up k equal 1000, well, then means the level surface is 1000 over this is equal 1000. So level surface x squared plus y squared plus z squared equal 1. So that's this kind of green things here inside. When you pick up k equal 250, well, then you have 1000 over this is 250. It means x squared plus y squared plus z is equal 4. Then you have this green circle here. So those are the levels, the kind of level surfaces, kind of, yeah, again. But application is, this function describes the temperature at any point in space outside the unit sphere. Now, kind of this kind of in thermodynamics or in physics, kind of this terminology is that the level surfaces of this function is called isotherms. Isotherms means that the same temperature on the surface. That's the reason for isotherms. So that's the terminology they used kind of when they discuss kind of heat distribution and so on, kind of, or temperature distribution. Okay. So this is, I think that's the last slide. Yeah. Yes. So, okay. So this was 11.1. As I mentioned, this will not be on the test. And Monday we will have test review. So I will just kind of look at this kind of test review I put on the on Canvas, and also kind of just I will look at some homework problems. So the best preparation for the test is just solve all web work problems, because the test will look like web work problems. All problems on test will look like web work problems. I'm using web work to give a test, and all problems will look like web work problem. But okay, so that's all for today. And Monday, there's nothing new, just test 1 review. Okay, that's all.
Thank you, Professor. Have a nice day.
Okay, so see you Monday. Thank you.
Thank you, Professor.
Mm-hmm.
Thank you.
Thank you, Professor.
Thank you.